final question of the midterm, and we want to expand the function f of x in a appropriate Fourier expansion, essentially. So we have a piecewise function here, x minus 1, x plus 1, and on the left I've sketched a little bit of basically what this piecewise looks like. And so we want to determine, since doing the full Fourier series is going to take a very long time, or well, not very long, but it's very tedious, and you could definitely do it, but if you can take a shortcut, we may as well. So all we have to do really is determine whether we want to use an odd expansion or an even expansion, in other words, a cosine or sine expansion, and all we have to do that is we want to determine whether the function is odd or even. So let's go ahead and do that. So let's just go ahead and determine that. So if we do f of negative x, so if we do f of negative x, negative x for the following function x minus 1, right, we'll have negative x minus 1, and this is going to be equal to negative x minus 1, which is equal to negative f of x, right? So it's odd. Now let's do the same for the other part of the function. So we'll have negative x plus 1, which is equal to negative x plus 1, and this is also equal to negative f of x, meaning it is odd. So we can pretty much conclude that this piecewise function is odd. We can also tell that it's odd just by the symmetry. We can see that it's symmetrical upon the y-axis. So now that we know that we have to use an odd expansion, what is the formula for this? Okay, so the formula that we have to use for this Fourier series is f of x is equal to the Riemann sum, and it equals to 1 to infinity for b of n sine n pi over p x, where essentially b of n is equal to 2 over p integral from p to 0 of f of x sine n pi over p x dx. So that's what b of n is. So in order to find our Fourier series, we're going to have to find this first. So let's go ahead and start solving for b of n. But before we can start solving for that, we need to know what p is. And essentially, in the Fourier series, is just the period. We usually, when we're doing the full Fourier series, we go from negative p to p, which this right here would be negative p. This right here would be the positive p. So our p is essentially pi. There we go. So now we can start solving for b of n. So bn is equal to 2 over pi integral from pi to 0 of f of x, and our f of x in this interval from 0 to pi is x plus 1. So we'll write x plus 1, and then sine n pi over pi. Obviously the pi's are just going to cancel out, leaving us with nx, and it's dx. So now what we want to do is we want to distribute this sine nx into the brackets of x and 1. So if we do this, we'll get x sine nx dx. We're going to split these integrals, plus sine nx dx. There we go. So now we know that the integration for this is awfully simple. This would just be equal to negative 1 over n cos nx. That would be the integration for that. Now what about this right here though? For here we're going to have to use integration by parts. So our u is going to be equal to x. Our dv is going to be equal to sine nx dx. So this means our du is just going to be equal to the derivative of x, which is 1, so du is equal to dx, and our v is just going to be equal to the integral of sine nx, which would be negative 1 over n cos nx. There we go. So now we just need to do the by parts formula, which would be u times v minus integral of v du So let's go ahead and actually do that separately first. So u times v, so basically negative x over n cos nx minus the integral of negative 1 over n cos nx dx, which we can just take out the negative 1 over n as it's technically just a constant. So plus 1 over nx, and then we're left with just cos nx in the integral, which we can then further evaluate to give us negative x over n cos nx plus 1 over n squared sine nx. As so. So now we found the integration for both parts. We're still going to need to evaluate it from pi to 0 separately. So let's go ahead and do that then. So we need to evaluate this from pi to 0. Pi to 0. So if we want to evaluate this from pi to 0, let's plug in pi first. We know that sine of pi is going to be 0, so there's no bother writing that, and it's subtracted by 0. And we know sine of 0 is also going to be 0, so it's just minus 0. So essentially all we get here is negative pi over n cos n pi. And let's go back to this following integral here, and let's evaluate that from pi to 0. We'll get negative pi over n cos n pi minus, we know that this is going to be 0 since, oh sorry, no, it should not be pi, it should be 1 over n. So we'll have negative 1 over n cos 0, and we know that cos of 0 is equal to 1, so we can just write that, and since it's a negative, this cancels out to give us positive, so we would have plus 1 over n. There we go. So let's plug these back into our, our b of n that we're solving for. So let's not forget we're solving for bn. And we have 2 over pi still outside. So what we're left with is negative pi over n cos n pi. And this is going to be subtracted by 1 over n cos n pi, and then plus 1 over n. So now what we can do is we could factor out a 1 over n. So let's go ahead and just factor out a 1 over n. So this means we'll have 2 over n pi, and what we're also going to do is we'll factor out the negative while we're at it. So this means we'll have pi cos n pi plus cos n pi minus 1. Now what we'll do is we want to factor the cos n pi inside the brackets, which is inside the negative. So we'll have 2 n pi negative and then brackets. So we factor out that cos n pi, and this will leave us with pi plus 1, and it's minus 1. Let's distribute this negative back. So we'll essentially have 1 minus cos n pi plus 1. And our final step is that we can convert cos n pi into negative 1 to the power of n. So our b of n is equal to 2 over n pi 1 minus pi plus 1 negative 1 to the power of n. So we found our b of n. So we're pretty much done. All we have to do is now plug it back into the actual formula, which I listed right here. Let's go ahead and do that now. So our b of n, 2 over n pi 1 minus pi plus 1 times negative 1 to the power of n, and then sine nx. And that is the Fourier series for this piecewise function.